In class, we went through the derivation of the equation for the velocity necessary to hold a car on a curve regardless of friction. This is an ideal velocity. It represents one velocity for going around the curve, and at that one velocity, the car, even with very smooth ice, frictionless surface, should be able to remain on the curve without any assistance from friction. However, at other velocities, friction is going to come into play. In this diagram, we've got a car, beautifully drawn car, coming toward us. This is the cross-section of a banked curve. We've got some forces labeled here, or drawn in. This would represent our normal force, and this would represent our weight, or mg. We also have a theta here. We can also say that if the car is moving, depending on the variation from that ideal velocity, we may end up with a car moving up the bank or down the bank, depending on the velocity that's there. So in other words, it could slip down the bank, or it could rise up the bank and eventually go off the curve. So we really want to look at a couple of different scenarios. First of all, if we have the velocity of the car less than the ideal, so in other words, it's moving too slow. In that situation, we can come in and draw a velocity vector, or the velocity is too slow, so it's actually going to slip down the bank. So we have the car in this case moving down the bank because it's too slow. That's going to cause it to have friction. If it's sliding down the bank, friction is going to be in this direction. We'll call that FF. Another scenario involves the V car greater than ideal. In that case, going too fast, and as it rises and eventually goes off the bank, if it gets faster and faster, our friction is going to be in this direction. So our issue is that we have, depending on the velocity, we may not have one direction of friction. It may be too fast or too slow, but the ideal velocity is that one that will hold it on the curve regardless of the actual velocity, regardless of the actual surface. And that represents one velocity, and then we can go above or below that, and in each of those cases we're going to have friction involved in the problem solving. So what we would like to do today is to try to derive the equation for the velocity of the car that would be considered safe for a banked curve with friction. So what that should give us is a V max, or how fast is fast enough to stay on the track or stay on the curve, and also a V min, which would be the minimum slow speed to keep from slipping off on the other side. So this gives us a range of velocities, and that range of velocities could be used, for instance, in calculating speed limits as an example. So let's begin by drawing a free body diagram for a scenario where the velocity of the car is greater than the velocity ideal. Let's begin by drawing a free body diagram. In our free body diagram, we're basically mimicking what we had on the previous slide for the car. We've got our normal force. We've got mg, and if we've got friction down the ramp, then we're going to have friction in this direction, not necessarily drawn to scale. In this scenario, what we've got is our x and y axis are drawn as usual. So our x-axis is horizontal and our y-axis is vertical. We're not using the ramp surface or the curved surface like we did with ramps, where one of our axes was tilted. It can be done that way, but this is probably the easier way to go with this. Okay, we also have some components to vectors. We have for the normal force, we have two components, and also for the friction force, we have two components. We can label our components. This is F normal. This is, and by the way, this is theta, and this is also theta. And they are the same angle, and obviously they're not here, but they would be in the scenario that we're drawing. So this would be F sine theta, and let me reverse something there, F normal sine theta. And this would be F normal cosine theta. This would be F friction, FF. So this would be F sine theta. And this would be F cosine theta. And then this is the weight, or mg. Okay, we're going to start out by finding a sum of forces in the y. Okay, our forces in the y include the weight, the y component of the normal force, and the y component of friction. Okay? You'll also notice here that we have two components to centripetal force. If this is toward the center of the circle, this one's toward the center of the circle, and this one's in the same direction. So the normal force and friction are both contributing to centripetal force. Okay, so our sum of forces in the y equal Fn cosine theta plus, I'm going to put this as a negative mg, because we know g is negative, plus our y component of the friction also, which is going to be the negative of FF sine theta. The car is not accelerating in the y dimension, so we would call this all equivalent to 0, constant velocity motion in that dimension. We can rearrange, since these two are negative, we can add them to the other side, to the 0, and say that Fn cosine theta equals positive mg plus force of friction sine theta. We know that the force of friction is equal to mu times the normal force. So with that we can say that, rewrite this equation, Fn cosine theta equals mg time plus mu F normal sine theta. And then of course we can also rewrite the equation so that we have like terms. Fn is the term that I'm looking at, so I could rewrite the equation to say that mg is equal to Fn cosine theta minus mu Fn sine theta, and we can factor out the Fn and say Fn times cosine theta minus mu sine theta equals mg. And then Fn is equal to mg divided by cosine theta minus mu sine theta. Okay? And that becomes an equation for later. Okay, so that's the first part of the derivation. The second part of the derivation, we're going to find the sum of forces in the x. So we start by saying sum of forces in the x. If we look back at our diagram, we've got a couple of forces in the x. We've got Fn sine theta or the x component of the normal force, and we've also got the x component of the friction force, F friction cosine theta. Okay. We can rewrite and say that sum of forces is equal to Fn sine theta plus renaming force of friction as mu F normal, like we did above, up here, cosine theta. We then factor out an Fn and say sum of forces in the x equals Fn times sine theta plus mu cosine theta. Okay. We can substitute in our value for Fn that we have here and say sum of forces in the x equals mg over cosine theta minus mu sine theta times sine theta plus mu cosine theta. Okay. And simplifying this a little bit, making it look a little bit better, sum of forces in the x equals mg times sine theta plus mu cosine theta over cosine theta minus mu sine theta. Now, the equation could be used like this to go ahead to velocity, but I'm going to make a little change here. I'm going to transform our fraction here by multiplying the numerator and denominator of the fraction by 1 over cosine. I've got sine theta plus mu cosine theta over cosine theta minus mu sine theta. I'm going to multiply each of these by 1 over cosine theta. Okay, that gives sine theta over cosine theta plus mu cosine theta over cosine theta over cosine theta over cosine theta minus mu sine theta over cosine theta. Now, this is going to, let's look at what this reduces to. Sine theta over cosine theta is tangent theta. Cosine theta over cosine theta cancels to 1, so that's plus 1 mu, divided by cosine theta over cosine theta cancels to 1, minus mu sine theta over cosine theta. Sine theta over cosine theta is tangent theta, so mu tangent theta. So I said this last step isn't entirely necessary, but it actually produces an equation that you would normally see in most textbooks by going through this extra step. So now that becomes, putting it all back together again, because all I was dealing with was the fraction there. Fx equals mg times tangent theta plus mu over 1 minus mu tangent theta. Almost there. Now, we know that the sum of forces is equal to, sum of forces equals F net. And in this case, since we have circular motion, or motion around a circular path, we've got mv squared over r, or centripetal force. So we can say mv squared over r equals mg times tangent theta plus mu over 1 minus mu tangent theta. Okay. We're trying to solve for velocity, in case you've forgotten at this point what we were even solving for. So this is what we're shooting for. Our m's are going to cancel as we divide away the m. We're going to cross multiply the r and get v squared equals r times g times tan theta minus plus mu over 1 minus mu tangent theta. And of course we need to take a square root for that, so taking the square root of both sides, we get v equals the square root of rg times tangent theta plus mu divided by 1 minus mu tangent theta. Okay. Now, let's think about what this means again. This velocity, we go all the way back up. In this case, we had the velocity of the car was greater than the ideal velocity. So if we go back here, that means we're too fast. So in this case, we've got a velocity that's going to cause the car to begin sliding up the ramp, or moving up the ramp, and friction is not going to be able to hold it in place beyond that. This is a maximum speed, a fastest speed, and the friction, of course, will be directed down the ramp in that case. And a component of that, the x dimension, would be one of the components of centripetal force. Okay, so if we come back to this, if we make, let's call the blue in this case the maximum velocity, what would we do to get the minimum velocity? Well, to get the minimum velocity, you can go back through this derivation again, and it's great to go through it a second time, but what ends up happening is the only thing that changes is our sign. So let's call red the minimum v. And if we go back through all of this, what we'll find is that when we get down to this point, and I actually should have done it here. So we get a plus or minus situation. so that if we have the square root of rg times tan theta minus mu divided by 1 plus mu tangent theta, that's going to give us the minimum velocity. If we have square root of rg times tan theta plus mu divided by 1 minus mu tangent theta, we get the maximum velocity. So that gives us our velocity range. Plus or minus.